Okay, so here's what we were talking about last time. We were talking about directional derivatives. Here's our definition of directional derivative. And remember, the idea of a directional derivative it's pretty fundamental to the idea of a derivative. Namely, look, we suppose a scenario where we're at a certain point in the domain moving with a certain velocity. We have an input rate of change, and we would like to know, big surprise, we would like to know the corresponding output point. What is its output velocity? It's a very, very natural thing to want to talk about. Right. So anyway, how to compute this for sufficiently nice functions. This formula is just a direct construction of, let's manufacture a scenario where we're moving with that velocity, and then let's directly compute what the corresponding output velocity is. Okay, so we saw examples of how to compute this, etc. Then we talked about a related idea, and that is of unit directional derivatives. Unit directional derivatives, they're based on this idea that directional derivatives are scalar multiplicative. You can factor out a scalar at your leisure. And then you make the clever observation, well, let's just factor out the magnitude. And then we get this neat property that this thing that I want to call a unit directional derivative, that's the thing that you multiply by speed in the domain to get velocity in the target. Now, so that recovers, again, one of our points of view on derivatives, which was that derivative is something that you do to. It's a factor. It's something you do to an input change to get an output change. This kind of recovers that sort of structure. Sort of. Right, but confession. Of course, this is not really the input velocity. This is just the magnitude of the input velocity. So it's a little forced, to be honest. Here's a sort of a picture of how to think about the unit directional derivative. And just like we were saying, if you were moving with a certain velocity in the domain, then the unit directional derivative is the thing that you multiply by the speed in the domain to get the velocity in the target. Right? Just like it says. Right? So, which is better? Directional derivative or unit directional derivative? Well, they're just different things. They have different interpretations. And by the way, don't forget the fact that this unit directional derivative, this thing here, is, among other things, also a directional derivative. It's a directional derivative assuming that your input velocity is simply a unit vector. So it is a directional derivative as well. It's not the directional derivative with that velocity, of course. It's the directional derivative with the unit vector velocity. But anyway. Okay, so the big thing to remember is in this relationship here, remember it's all about the scalar multiplicativity, and so we have a relationship between these two things. Sometimes you find yourself wanting to know a directional derivative, in which case, if it is convenient, and by the way, no obligation, don't do this if you don't have to, if it's not convenient for you. But if it should sometimes be convenient, and it is sometimes more convenient to compute the unit directional derivative, cool, go ahead, compute that unit directional derivative, and then multiply by the speed to get the directional derivative that you want. It also goes the other way sometimes. Sometimes you find yourself, for whatever reason, and we'll talk about that in a moment, wanting to know the unit directional derivative. But it might actually be easier in some circumstances to compute a non-unit directional derivative. And if so, no problem. Divide by the velocity to then compute the unit directional derivative that you want. Right? So use this relationship, channel your inner laziness. Right? Use it however is going to make your life easiest. But don't feel obligated to do one or the other. One weird thing that I have noticed happening, some students sort of assume that anything is presented later in the course must be the new and improved, derivatives 3.0, and that's got to be better than derivatives 2.0 or something like that. I don't know. And therefore, always, anytime they need to compute a directional derivative, they always do it with unit directional derivatives. This is silly, right? There's no need for that. You don't have to if you don't want to. Do whichever one is actually easier. So let's see some examples. One more thing I need to talk about, and then we'll get to some examples. Okay, so there is another nice interpretation of unit directional derivative. As of the moment, the main pitch that I've given you, pro-unit directional derivative, is that it recovers this sort of factor structure. It's what you multiply by that to get that, and that's nice aesthetically in a way. But here's another one, and this next one is actually pretty cool. Let's suppose we're in this scenario here where we're looking at a graph. Graph. Now, again, your ears should perk up. Anytime you hear that word graph, you should think, oh, hey, whoa, this is, that's a little weird. It's familiar. This is how we used to look at functions, but this is now no longer to be assumed how we're always looking at functions. But suppose you were anyway. Suppose you're looking at a graph of some function. Right, like this. If you were to, in the domain, have a point and a direction, thus defining a line, and if you were to look at the cross-section in that line, that cross-section curve on the graph, cross-section by that vertical plane defined by that unit vector. Right, and then if you were then to look at the tangent line to that curve, kind of bringing back memories of single variable calculus. Right, we're looking at a graph and a tangent line, and we're about to ask what is the slope of that tangent line. Then the answer is that it's the unit directional derivative. Specifically, the unit directional derivative. You can't just pick any vector you want. Don't, for crying out loud, don't just pick some random vector pointing in the appropriate direction. It's got to be a unit vector specifically. Unit vector if you want to get that slope. And this is a really easy result to see. In fact, we kind of already have the equation written down. It's this one right here. The unit directional derivative, there it is, right? It's the thing that you multiply by input changes to get output changes, or said differently, the change in the height. Don't forget we're looking at a graph. When you're looking at a graph, the value of the function is the height as I have it drawn there anyway. And magnitude of delta x is the which I guess you might call the run, right? So we have the rise and there's the run, and if you just think of this as being a fraction, it's the rise over the run, it's the slope. Okay, so pretty straightforward. Back to this picture. Let's see how that looks. If we were to imagine that we, in that unit vector direction, that we move a certain amount. I didn't draw a straight line there. You move a certain amount in that direction, and let's say, so there's parallel. So looking at this triangle, there's the rise. And there's the run. So the rise over the run is the slope, is the unit directional derivative. So that is a nice perk. Okay, now let's see some examples. Let's see here. We're going to start off with a silly scenario where our friend Bob is walking around in a forest, and there are mosquitoes in the forest, and somehow, and let's not question the premise here, but somehow he knows the exact function, giving us mosquito concentration as a function of position, right? And he's opposed to mosquitoes, by the way. Nobody likes mosquitoes. So he'd like to know, okay, very reasonably, if he's moving 3.5 miles an hour due west, walking along some trail or whatever, how fast is the mosquito concentration changing? That's a pretty interesting question to want to know. Now, the answer to this question is pretty straightforward. We want to know the rate of change of a function. That is a directional derivative. So right off the bat, we know what we want to compute as a directional derivative. I, however, am going to compute this with a unit directional derivative. So specifically, the directional derivative I'm going to compute as speed times unit directional derivative. Now, why would I do such a thing? The reason I would do such a thing is because if you look at our velocity vector, let me write it down here. What is the velocity vector? The velocity vector, well, he's moving due west at 3.5 miles per hour. Due west, let's see, that way. So he's moving in the sort of the negative x direction, but with a magnitude of 3.5. So his velocity is negative 3.5, 0. Now, I could take that and I could plug in that velocity, plug it right into the directional derivative formula, and then carrying through that entire calculation, I would have a fraction that would be inside of my a plus tv, and then I'd be plugging in that fraction into f, and it'd just be fractions all over the place. Now, it's not such a bad fraction. I could rewrite it as 7 halves. 2 in the denominator is not that bad. But what if instead of 3.5, what if it was 3.68213? Something weird like that, right? Now you've got a nasty decimal that's sitting there carrying through your entire calculation. Extremely annoying and inconvenient. So the idea then is to interpret out of this that the corresponding unit vector is negative 1, 0, and then just, like I was saying, just multiply by the speed on the outside. We're just factoring out that speed. So the benefit of using the unit directional derivative then is when I actually get around to computing, notice all of this calculation that goes into computing this unit directional derivative, well, I get the benefit of using this convenient unit vector. And that is a convenient vector in the sense that it makes that coefficient really nice. There's no ugly fraction there. It's just 1. So it makes the calculation go down easier in this case. Now, if you were to just straight up compute the directional derivative instead, you would get the exact same answer. It's not getting you a different answer. It's getting you an alternative and I think easier way to get to that answer. Okay. All right. Next question. We have an ant walking around on a surface. Not a crazy scenario. Ant walking around on a surface. We're looking at the graph of this function here. That's our surface. And when the ant is on the graph, above the point 2, 0, he starts walking in a certain direction. Now notice I'm giving you that direction as a vector, so he's walking parallel to that vector from that starting point, 2, 0. Right? And here's a reasonable question that again we might want to know: what's the slope of the path that the ant is walking on? So here's a surface. And in the domain down here, he's walking in a certain direction, so he's going to be walking along a certain path. What's the slope of the tangent line? How steep is his walk as he walks along there? Well, slope is unit directional derivative. Right, we saw that a couple pages back. So notice here, in this question, I'm not trying to compute a directional derivative. That's not my goal. Unit directional derivative here is not going to be a sort of a convenient tool for computing something more important. Here the unit directional derivative is the thing that's more important. This is what we want. Okay, fine, and no problem. I can compute out what that unit direction or what that unit vector is. Here it is. There's that unit vector. And here notice that vector. The unit vector in this case is the one that's ugly and annoying. Right? It's got square roots in the denominator, for crying out loud. That's no fun. Right? So, again, channel our inner laziness. Can we think of some way to sort of outsmart this situation where I have to deal with algebraic annoyances? And yeah, let's factor out the annoyance this time turning a unit vector into a non-unit vector. That's the big idea. Right? So even though the unit directional derivative is what I want to compute, I'm going to compute that by factoring out this square root of 2 and then computing the resulting directional derivative that has these nice, easy coefficients of 1 and 1, right? I'm going to compute the directional derivative sort of directly, no pun intended. And that, again, notice my coefficients, just like I would like. These coefficients are nice and integer. Yeah? Everybody on board? Okay. All right. Okay, again, if you just did this directly using that vector, you'd still get the same answer. It'd just be more sort of algebraic annoyance. Okay. All right. So we've seen examples of how to go either way. We've seen examples of how you can use this to compute that, how you can use that to compute that. Let's recognize, though, that there are some situations where you don't need to do any of this. And so here's my example. Let's look at this scenario. I want to compute a directional derivative. Make up some story about temperature. I want to know how fast temperature is changing as I move in the domain in a certain way, whatever. And here's my velocity. And, go. What do I do? I have two choices. One thing that I could do is compute the directional derivative with my velocity vector being 2, 7 of my function f. My other option, I could try to use unit directional derivatives. And the thing is, my unit vector there would be 2 divided by the square root of 53, 7 divided by the square root of 53. And then take that unit directional derivative, look at these ugly numbers I'd have to deal with, and then having done that, I would then need to multiply by the square root of 53. So now, which of these would you rather do? You want to do the one with the integers? Or do you want to divide by a radical and then subsequently just multiply by that same radical for no gain? Gives you the same answer, right? Same answer either way. So I think the choice is clear here. Of course you'd want to do it that way. So again, don't make this mistake of thinking that somehow there's something more moral or proper about using unit directional derivatives to compute things. If you want the directional derivative, great, go ahead. Only use the unit directional derivative if it is either what you need or if it makes your life easier in one way or the other. Okay. All right. Okay, so unit directional derivatives are a special case of directional derivatives, and now we're going to see another special case. We're going to see a special case of that special case. We're going to consider now, what if the unit directional derivative that I want to compute, what if that unit vector u is an even better vector? Not only does it have magnitude equal to 1, but suppose it's a standard basis vector. About the easiest vectors you can imagine. What happens? It turns out that something nice happens. Computationally, extremely convenient computationally. So I'm just going to carry you through this calculation. It's just a little bit of algebra. But here we go. There's our definition of a directional derivative. Now notice that's just plain old garden variety definition of a directional derivative. I am recognizing that my velocity vector is that standard basis vector. And now, of course, if you have a derivative, derivatives are represented with limits. Now I want you all to think that through. Make sure you're comfortable with this. That is the, if you go back to Calc 1, the definition of the derivative, that S derivative there, written as a limit, is this limit. Okay. And now let's expand this out in coordinates. A is that. This standard basis vector looks something like that. There's this 1 in the ith position, right? So this I here tells me where that 1 goes. It's just a recopy. And now let's combine these vectors into a single vector like that. So what have we accomplished? I've shown that this special standard basis vector unit directional derivative is computed by that limit. And it turns out that there's a really great interpretation of this. I want to look carefully at what we have here, this formula here. And notice, for one thing, it looks a lot like the definition of a single variable derivative. But in fact, it looks scarily like a single variable derivative. In fact, imagine a certain scenario. This function f, now that's a function of a bunch of different variables. Right? Let's suppose that I were to change that function. Let's suppose that I were to stipulate that, look, I'm thinking about this function f, but I'm going to insist that all but one of the variables are fixed and not allowed to change. It's my scenario. I can make up whatever rules I want. In my little scenario I'm creating, f, it has a bunch of inputs, but all of those inputs are not allowed to change except this one. Just that one is allowed to change. Right? So if all of those variables are fixed, and I'm going to use gray to represent that they're fixed, notice A1 is not changing in this formula. A1's the same on both sides of the subtraction. Ditto all these other variables. Ditto all these other variables. The vast majority of these variables going into this formula are the same on both sides of the subtraction. In fact, there's only one variable that is actually changing there. Right? So what in this expression that I have, when I'm plugging in there, there's really, in practice, actually only one actual variable. Because that ith variable is the only one that's actually changing. So not only does this look like a single variable derivative, it is literally a single variable derivative at this point. Right? I've got this now single variable function called f. Side note, don't forget, we're made up a new rule, f, all these various inputs, only one of them is actually allowed to change, namely specifically that ith one. Everything else is stapled to the floor, right? Not allowed to change, fixed constant. So f now has only, per my decree, one variable. This is a single variable function, and this is the derivative of a single variable function. Now, why do we care about that? And the answer is because we have tons and tons of rules for how to compute single variable derivatives. Right? Product rule, quotient rule, chain rule, all that business. Right? So these special new derivatives that we've come up with, they're directional derivatives. Careful. They are unit, in fact, even better than that. They are standard basis vector unit directional derivatives. Product rule, chain rule, quotient rule. We can use all our old friend rules in computing them. So that makes these really interesting because, again, they make our lives simple. So that's a good thing. Look at how easy it is to compute these things. Here we go. Here's a function. There's a function of two variables, right? X and Y. But I want to take one of these special new derivatives where my input velocity is a standard basis vector. That means that x is the only variable that's changing. That means that this function I have highlighted in green, it looks like a function of two variables, but for what we're doing here, it's actually not. And now it's a function of one variable. It's a function of just x. So I'm going to take the derivative of that green function there by a very convenient process, which is to say, it's just a function of only x. So I have here variable, but the other variable, y, constant. So all the rest of that stuff is constant, and in the process of taking that derivative with respect to, the one variable x, I'm going to treat it like a constant. So the derivative of the x squared, of course, is 2x, and everything else just kind of comes along for the ride. The derivative of x squared times a constant is 2x times that same constant. Then the derivative of this constant, well, that's just 0. Right? Really easy to take derivatives. Okay. This is shockingly good news. Here's how good this news is. Computing these kinds of derivatives, I haven't given them a name yet, I know. But these kinds of derivatives, computing them is even easier than single variable derivatives. Because when I'm taking these special kinds of derivatives, not only do I get to use all my single variable calculus rules, but I also get to just say, you know what, I'm going to treat that like a constant. Boop. Right? I get to ignore huge amounts of my function that I'm taking a derivative of. World's easiest derivatives to compute. Okay. All right. So name and notation. These are called partial derivatives. Y'all saw that on the title of the section. Here's the definition of a partial derivative. A partial derivative is one of these special directional derivatives. I point out that it's computed with that limit just for sort of as a reminder. But most important thing to remember about partial derivatives is that they are directional derivatives. Special directional derivatives. Here's a notation that we use. This notation right here for partial derivative. Be careful when you're writing this little symbol right there. That little symbol, it's not a D. Please don't write a D. In fact, if you write a D, it is in fact wrong. Right? D, in this setting, if you were to write df over dx, you would be saying that f really is and only can be a single variable function. Well, that's not true. Right? F comes to you with multiple input variables. Right? So using this special symbol, this partial symbol there, using that special symbol says, I'm going to impose upon this function that only a certain variable is allowed to change, only xi is allowed to change. And then subsequent to having made that choice, I'm going to compute a derivative. Right, so you have to use the partial symbol. Can't emphasize that enough. There's a tendency for students to kind of, we've talked about this before, with spherical coordinates. There's a tendency for students to write P instead. And again, you can't do that. That's a different symbol. It means a different thing. And likewise, don't make it a D. So you kind of got to practice making this new symbol. It looks a lot like a sort of an upside down row, kind of. But don't take that too seriously. Anyway, be careful with that. Some other notations, by the way. So recall that in single variable calculus, let me switch to a better color. In single variable calculus, if you have f, then you can take a derivative by writing prime, or you can write df dx. Right. So analogously, then, if you're looking at a partial derivative, this Leibniz-like notation for derivatives, there is a Newton-like notation for partial derivatives as well. I can't just say prime, because if I were to say prime, that doesn't indicate which variable specifically you're taking a partial derivative with respect to, right? So if you want to use this, kind of prime-like notation, don't ask me why, but they use it as a subscript instead of a superscript. Just make a subscript indicating the variable that you're taking the partial with respect to, and this is an alternative notation then for partial derivative. And then, of course, likewise, if you give a name to your output variable, if you were to call it, if the name of your output variable is z, you can write z prime in single variable calculus. It's understood that primes means derivative. Likewise, here you could write zx, and this is going to be a convenient notation in lots of circumstances. Okay. Alrighty. Very quickly, let me talk about the interpretations of the partial derivative. again, most important thing, the partial derivative is a directional derivative. So you treat it just like a directional derivative because it is a directional derivative. It is also, of course, a special case of the unit directional derivative. So treat it just like a unit directional derivative. And remember, unit directional derivatives have this additional interpretation as being slope of the tangent line to the curve. That's the cross-section of the graph of the function. Lots of little asterisks on this last interpretation there. Okay, couple of quick examples. This first example, this one kind of jumps right in the boat. But I want to know what's the slope of the tangent line, the cross section of the graph of the function, right? So, I mean, the phrasing of this question is this blaringly obvious reference to that interpretation that we just talked about. Specifically, cross section in the x direction. And so because we're looking at a slope in the x direction, we're going to be taking, well, a partial derivative, and since we're in the x direction, partial derivative with respect to x. So you're just taking a partial with respect to x. And the algebra on that is, again, very straightforward. Taking a partial derivative with respect to x, so that means that x is a variable, means that y is a constant, and so most of the function, constant. Right? And so the derivative is really easy to compute. The derivative of that term, well, of course, the x squared's derivative is 2x. The factor of y cubed, being as it is a constant, just comes down, remains as a factor. The derivative of this term, well, it's a constant. Its derivative is 0. Okay, so world's easiest derivatives. Here's another question. Looks like a directional derivative problem at a glance, but we've got a function describing physical matter. So humidity is a function of location, whatever. Right? We want to know how fast is the humidity changing as a bird flies through the air. Okay. Well, how fast a function is changing is a directional derivative. So this, like I say, at a glance, it looks like a directional derivative problem. Then we realize that I can, of course, rewrite this as a unit directional derivative based on the fact that the velocity vector, factor out that 5 and it becomes a nicer vector. Right? And then you notice that the resulting unit directional derivative is a partial derivative. And so, what this boils down to is just taking a partial derivative of this function with respect to a single input variable. Now, wait a second. What input variable? Careful. That velocity vector, that's in the direction of the y-axis, right? So this E2 is a standard basis vector in the y direction, so we take a partial with respect to y. Everybody happy? Okay. Second derivatives. I don't think any of this is going to be a surprise to anybody. So notice, here's a multivariable function. Let's take a couple of partial derivatives. There's the x partial, there's the y partial. Check it out. They themselves are also multivariable functions. And I could talk about taking a partial derivative of one of these partial derivatives. Just like we did in single variable calculus. Right? So no big deal. Let's take the x partial of this x partial of f. Same rules. No tricky curves there. Okay. Likewise, you can take a y partial of the x partial of the x partial of the y partial, whatever. Okay. Do be careful with one thing. The notation, again, it's easy to get this backwards. Notice when I write let me look at this one. When I write this partial derivative, notice it is the x partial that I'm computing first, and it is the y partial that I'm doing second. And so correspondingly, now there's this other notation for a for a second partial, and it's a little clunky. We combine those two partial symbols and say partial squared. It's ultra awkward. Don't interpret that too literally. We're not actually squaring anything, right? But there's a partial and then there's another partial. Just symbolically, it looks like two factors, so let's just write it like that for symbolic purposes. And then notice that factors naturally ought to get written down like that. And so when you see this notation, here for a second partial, that's the one that you take first, and that is the one that you're taking second. And it looks backwards. It's right to left instead of left to right. So careful. Okay. What does this look like? Let's take a look here. We have a graph. This is z equals some function of x and y. And let's take a partial derivative, a second partial with respect to y. Oh, here, I'll do it like this. So let's take that second partial. What do we get? Okay. Two-step process. First, for the purposes of the first y partial, I'm looking at a cross-section in the y direction. That cross-section looks something like that, and I'm looking at the slope of that tangent line. Having done that, I then want to, continue to look in the y direction. In other words, stay in that plane. Continue to view x as being constant, right? So, for the purposes of this entire calculation, both for the first partial that we're taking and for the second partial that we're taking, all along we're treating x as if it's a constant. So here's another way to say this. Another way to say this is that when you're doing this second partial, you are first looking in that plane where y is the only variable. So first you're looking in the x, a plane perpendicular to the x-axis, and then in this plane, you're just taking a second partial, a single variable derivative, second partial. It is literally a single variable derivative because, again, x is being treated as a constant, so the interpretation is exactly the same as it was in single variable calculus. It's just the concavity. Right? So as I have it drawn here, that cross-section curve is concave up. So this second derivative with the second partial with respect to y is positive. Very natural. Okay. But what if we were doing things a little bit differently? What if we were taking a partial of f with respect to, let's see, let me cheat here. Yeah, taking a partial derivative with respect to x, let's say, and then suppose I wanted to take a y partial of that. In other words, what if I was doing a mixed, what we call a mixed partial? Bad news. It does not break down like it did in single variable calculus. Because for the purposes of this part of the calculation, while you're taking the x partial, you're treating y as being a constant. But then you're no longer treating y as being a constant. Here, now you're treating x as being a constant and letting y be the variable. And so we cannot just say, it's just like single variable, and one of these variables is constant. So we have a harder problem. Mixed partials are harder to understand. Everybody see the snag? It's a matter of interpreting appropriately then. So here's the picture I like to draw, and there's no perfect picture of this, by the way. So here we go. We're going to look at the partial of f with respect to x, and then we're going to take the y partial of that. And let me just remind you, we have an interpretation of partial with respect to x. It is, straight lines. We're going to look in a plane where we treat y as a constant. In other words, a vertical plane vertical plane parallel to the x-axis, because we're going in the x direction. We're going to look at this slope of a tangent line. By the way, notice I didn't draw the graph. I think the graph would just really muddle up the picture too much. But we're going to be looking at a tangent line imagine there being a graph there. And we want to look at the slope of that tangent line. That's what the x partial is. The y partial, then, I'm going to interpret in a different way. Don't think slope when we're looking at the y partial. Think instead that, well, it's a directional derivative. So when we're taking this y partial, we're asking, as I move in the y direction, how is this function changing? Right, so how are the x slopes changing as I move in the y direction? And so what I have drawn here, this is going to be, it's going to turn into a mess if I sort of highlight the whole thing, but you can see as I move in the y direction, those slopes, all of those slopes are intended to be slopes in cross sections in the x direction. And you can see those slopes are changing. As I have it drawn there, they're decreasing. Right? So the slope, let me draw one of them. This slope here is positive, and then this slope here is negative. So as y changes, as you move in the y direction, I want to know how are these green slopes changing? Well, they are decreasing. So this thing here, and I don't have a three-dimensional model to show you, but it's like you've taken a surface and kind of put a twist in it. You see what I'm saying? Sort of a twisting of a surface. I always like to imagine that I've got a sheet of rubber, and that you're literally just twisting. Rotate one way on this side, rotate the opposite way on the other side. Right? That's sort of a twist, and you can imagine that surface would do kind of like this kind of a thing. Okay. So it's hard to visualize. Anyway, there is no single variable analog of a mixed second partial geometrically. Right, so new concept. Alrighty. One thing you might have noticed, going back up here to where we first did our calculations, did you notice that the y partial of the x partial and the x partial of the y partial happen to be the same? How about that? What are the odds? It turns out that this is not a coincidence. However, it is also not always true. So don't assume that this will always work out. Right? But it's true in a very broad set of circumstances. So mixed partials are independent of order. When a certain condition is satisfied, you need all of the second partials of that function to be continuous functions. And here's the good news. Very often we're dealing with functions that are like polynomials. All polynomials are continuous. You take derivatives of polynomials, you get, more polynomials. It's clearly continuous. Right? So this condition is very often satisfied. In fact, it takes a pretty weird manufactured example to find a case where this is not true. So it's usually true. Nevertheless, there is that asterisk. Okay. Alrighty. Okay, moving along. By the way, there's a bunch of short sections that we're passing through in the book at the moment, so I'm hoping, fingers crossed, on the possibility of maybe finishing, by the end of today, 4 sections of the book. We'll see if that happens. I don't know if it's actually going to happen, but it's possible. Okay. Summarize. What have we done so far? We've made a definition of a directional derivative. Right? You give me any direction, any velocity in the domain. No matter where you are, no matter what your velocity in the domain is, we have a formula that tells you how the function is changing. The values of the function are changing. You could make the speculation that, well, for crying out loud, that's fully general. And, What more could there possibly be to say about derivatives? And that's a very tempting thing to say, but it is not all we can say about derivatives. It turns out that even though this point of view on derivatives is very natural, it's very constructive. You want to know what a derivative is? Fine. Do the following. Bam, there's your answer. Right, we have a very constructive definition. It turns out that there's a lot of hidden structure, hidden truths that are packed away, invisible inside of this definition where you can't see them. And so we need to explore what's going on inside of these derivatives. So I'm not gonna do everything in this section. I'm gonna skip and do just sort of key ideas. There's a lot of details. It's a really entertaining for me. It's a really fascinating thing to explore, all the different kinds of differentiability and different ways in which a function can be nice. But we just don't have time for that in Math 212, unfortunately. So anyway, here's a couple of ideas. First, a quick example, just to kind of as a segue. Here's a function. Let's compute a directional derivative. The only thing that's new about this calculation is that in the computation of this directional derivative, I am not going to indicate exactly what the velocity vector is. I'm going to keep the velocity vector general. So we do have a specific given function, and we have a specific point from which we are computing. Okay, so we're going to look at this point A, 1, 2. But let's see, how does the directional derivative depend on the velocity? We haven't done that before, right? Every directional derivative that we've ever computed, A was a given point given by numbers, and V was a velocity given by numbers. So how does this directional derivative depend on velocity? Now, this is a straight up plug and chug. It's just calculation, right? And go ahead and do that. And here's what's interesting about the punchline. That directional derivative depends on the velocity by way of a linear formula. It's linear in the velocity. And we never noticed that before. Right? Now you might say, okay, well, yeah, but you picked an easy polynomial. A lot of students will say, well, yeah, sure, it's linear because look, your function is quadratic. Well, correction, the function is quadratic function of x. We're noticing how the directional derivative is a function of v, not x. So that's not the point. Right? In fact, and there's a tedious calculation that you can do here for, give me a general polynomial. It's hard to write down a general polynomial. But if you do and you wade through, oh my gosh, all of it, what you will find is that this works for every polynomial. All directional derivatives are linear in the velocity at a given fixed point, A. Okay. So, wow, that is a neat observation to make. In fact, this feature of directional derivatives being linear in the velocity, this is worth giving a name to. So the name that I give to this is, where did I write this down? Here it is, directional linear. Any function that has this feature that the directional derivative is a linear function of velocity, I'm going to call that a directional linear function. Okay, so what we saw above then is that all polynomials are directional linear. And there are many more functions that are directional linear. It turns out it's a surprisingly common property for functions to have. Okay, that's not all of the structure that there is to be found. There's more to say. It does get a little bit awkward here. Apologies, but I'm going to point to a definition of something called differentiability. But I'm not going to give a full discussion of differentiability. It's a hard conversation to have. It's really a harder conversation to have than multivariable limits. And ultimately, the gains, I'm arguing with myself, making tough choices about, we have so much time, only so much time, and what are y'all going to get the most out of? I don't think it's that the payoff is worth spending time on this. But I want you to be aware that there is this thing called differentiability, and that the requirement that there exists a linear transformation T such that this limit, this is a multivariable limit, is equal to 0. Note that this is a non-constructive definition. I'm not telling you what T is. I'm saying a function's differentiable. Well, if you can find a linear transformation T. No promises. Right? So, it's an awkward definition. But this is what it means for a function to be differentiable. And it's an eyebrow raiser because you look back at this idea of directional linear, and it's tempting to say, well, that's a pretty nice feature for a function to have, that I can compute all the derivatives with a linear transformation. How is that not the same as there's a linear transformation that has a certain nice property? And again, deep dive. It's more conversation than we have time to have. So I'm going to say, though, that they are different. It's important to know, though, that every differentiable function is directional linear. That's true fact. But beware, not every directional linear function is necessarily differentiable. And again, it's a deep dive, and we're not going to worry about that. Okay. So given this choice, given this comparison between these two conditions, why do we care about differentiability then? It's harder to talk about. It's less obviously natural. So how about, why wouldn't we just jettison this idea that I'm calling here differentiability? Why wouldn't we just spend our lives working with directional linearity? And the answer is that if you want to be able to talk about theorems, and what is the sharp condition, what is the weakest condition that you can write down that nevertheless still allows you to draw the conclusions you need to draw. So the perfect, best way to condition theorems in a very large number of cases, differentiability. The hard one to talk about is required, and directional linearity is not quite good enough. So that's annoying. But anyway. Okay, so this definition of differentiability, notice there is this linear transformation that's referred to. This linear transformation has to exist. If a function is differentiable, that linear transformation exists. If it exists, we can give it a name. And the name that we're going to give to it is the derivative transformation of f. We're going to write it like this. And the very first thing I'm going to tell you about the derivative transformation, it's hopefully good news. I think this is really good news. The derivative transformation, what it does to a velocity vector is it computes directional derivatives. So all this trouble that we're talking about we're going to reinterpret directional derivatives as linear transformations. Let's not lose sight of the fact that still what we're talking about are directional derivatives. Input velocity, output velocity. All that same stuff. Okay. We're just talking about it in a fancier way. I do think it's important to make this point here that even though, say it like this. Let's look at that equation right there. There's D's and F's and V's and A's on both sides of that equation. Right? So, aren't they kind of automatically the same? And I just want to point out they're not automatically the same. This side of the equation says, start at your point A, put on blinders, and look exactly and only in the direction of the vector V. I don't care. I couldn't care less what's going on anywhere else. I just want to know, as I'm going in the direction V, what's happening, how fast is the function changing as I move in that direction. Okay, so the right side of the equation, directional derivatives, that's a concept that has blinders on. It's very narrow and focused. Okay. The left side of the equation is not. This is a very broad perspective thing. This says, first, let's try to understand the function, and let's hope that there is a single tool that will allow me to understand the function, how it changes in every direction, in a universally satisfying way. That, again, we can't go into the details of that. But the function has to be nice in this powerful way first. And if the function is nice, then this is going to tell me how the function's changing as you move in the v direction. So they compute the same thing, but with this big condition on the left side. Okay. All right. So no surprise, again, the properties are just like the properties of directional derivative. Right? So the derivative transformation, in the same way that directional derivatives did, it turns input changes into output changes. It turns input velocities into output velocities. Just like directional derivatives. But here's where we recover, again, something really nice from single variable calculus. Remember, very first thing we talked about in this chapter is derivatives or relationships between input changes and output changes, and check it out. That's exactly what we have here. So this linear transformation, the derivative transformation, that is the thing that turns input changes into output changes. Right? Okay. So this is my nomination of, if you had to pick a single thing to call the derivative of a multivariable function, that's it. A lot of students would tell you partial derivatives. I think that's a mistake. Partial derivatives are very narrow. It's only looking in one direction. You have to have a bunch of them to even be able to pretend that you're looking in all directions. And again, they're only along axes, right? Partial derivatives are very, very limited point of view on derivatives. Directional derivatives. It's nice, but it's, again, sort of myopic. It's sort of, unidirectional, right? So then we've got unit directional derivatives as well, and now we have the derivative transformation, and we're going to see another one in a moment. Actually, two more. There's a lot of different kinds of derivatives in this class. But this is the big one. This is the important one. Derivatives are linear transformations that turn input vectors, input changes, into output vectors or output changes. Okay. All right. How are we doing? Is everybody on board? Any questions? All righty. Yeah. Okay. So here's our first example, and we already computed for this previous example here. We computed that all of the directional derivatives could be computed by this formula, and so here we have then. This is how we're going to write down the derivative transformation. The derivative transformation. We know that the derivative transformation, if it exists, which it does in this case, will compute directional derivatives, which we know are computed by that formula. So what we have then is that this linear transformation is computed by that formula, and then we can write down a matrix. Remember, our matrix shorthand for linear transformations, the matrix shorthand is just that matrix 2, 5. Yeah? Everybody good? All right. Okay. So, looming question. How do I know that the derivative transformation exists? I just got through talking about how delicate it is. It only exists if the function can be uniformly understood in all directions at the same time by a single object as described by some big complicated expression that we're not diving into. So how do you know in practice, day in and day out, that a function actually is differentiable and that therefore you can even do any of this? And the answer has to do with something called continuous differentiability. This is an unexpected lucky break. Now, I assume that y'all remember the idea of a function being continuously differentiable from Calc 1, yeah? Function's continuously differentiable if it's differentiable and that derivative is continuous. Very, very similar idea here. A multivariable function is continuously differentiable if the partial derivatives exist and are continuous. It's a total rip-off of the idea of continuous differentiability from Calc 1. It's easy to check. Look, it's based on partial derivatives. Partial derivatives are the world's easiest derivatives to compute. How do you check if something's continuous? Well, pretty much, if it's a function you can write down with the usual tools that we use to write down functions, and if something hasn't gone catastrophically wrong, it is continuous, right? So, it's very easy to check continuous differentiability. And then here's the unexpected, huge win. If a function is continuously differentiable, then that implies that it is differentiable. And that is a mysterious, an awesomely convenient little freebie, because continuously differentiable is easy to check, but differentiability is hard to check, right? So in practice, day in and day out, here's how you actually get stuff done. If you would like to use a derivative transformation, if you would like to, use a linear transformation to compute all your directional derivatives for you, which you want to do. If you want to use differentiability, just check and see, is the function continuously differentiable? Vast majority of cases they are. And then you cite this theorem and you're good. So that's, like I say, a huge win. You'll notice how we use that in this example here. By the way, this questions like this have been test questions in the past. You can look. Y'all have all my old midterms. But here's a multivariable function, and I ask, with a little bit of misdirection, I ask, is this function differentiable? And again, the purpose of a question like this is to see, who remembers the in practice, how do you actually get stuff done tool, which is the way you check differentiability is, oh my gosh, you don't go to the definition of differentiability. Good night. That's so hard to work with. No. Fingers crossed, hope that it's continuously differentiable. And so here we go. Here are the partial derivatives of the two different component functions. Those partial derivatives are all continuous. So this function is continuously differentiable. And then we cite the above theorem. This theorem says if it's continuously differentiable, then it's differentiable. And therefore the original function we were interested in is differentiable. Everybody see the strategy? Okay. All right. Again, I'm a little sad that we have to skip through the rest of this stuff. There's some really neato examples in here, and if anyone's curious, I would very much enjoy talking to any interested student about the subtle differences between these key counterexamples, and it's very weird and it's very geometrically interesting and brain stretching. But anyway, we're going to skip all that stuff. Okay, so on to the next thing. And this is really still just about differentiability. We've got this great tool, differentiability. It allows us to compute, if a function's differentiable, we can compute directional derivatives, answers to lots and lots of physical application questions. We can compute directional derivatives with a linear transformation. Natural next question. Okay, how are we going to write down that linear transformation in practice? And of course, we have an answer to that already. The way we write down linear transformations is with matrices. Right, that's the whole point of section 3.2. Linear transformations are hard to write down sometimes, and so a matrix is a nice shorthand for it. So, here we go. If you have a differentiable function, You want to capitalize on that, and you want to be able to compute the derivative transformation for that differentiable function. How are you going to compute that derivative transformation? Answer, with a matrix, of course. The matrix is called the Jacobian Matrix. We represent that with a J and subscripts indicating the function and the point that you're evaluating. That Jacobian Matrix is the tool. That's how you deal with, in practice, the way you actually, hands-on deal with derivative transformations is by their Jacobian Matrix, JF. Okay, so how do we compute Jacobian matrices then? This is a wonderfully convenient calculation. This is one of my favorite calculations in the subject. Don't forget, columns are images of standard basis vectors. Arguably, it's on the top 5 list of most important things to know about linear algebra. Columns are images of standard basis vectors. In fact, don't forget, this is the definition of a matrix. The columns are the images of the standard basis vectors. It is on this definition that all of the formulas that we have for how to multiply and how to add, all matrix algebra is consequences of this choice. Columns are images of standard basis vectors. And look how everything jumps into our lap then. If you want to compute a column of the Jacobian matrix, well, it's the image of the corresponding standard basis vector. Whoops, sorry, my highlighter did something weird there. Derivative transformations compute directional derivatives. That's a standard basis vector. Again, because columns are images of standard basis vectors. That means that the directional derivative is the directional derivative with the velocity being a standard basis vector, which means that this is a partial derivative, which is the world's easiest derivative to compute. And so it's great how this works out. We've been making all this kind of abstract, vague references to there's this mysterious linear transformation that will magically compute all of our directional derivatives for us. You're going to compute it with your favorite, easiest derivatives in the world, partial derivatives. That's totally awesome. All right, so let me. I love this. I love this little calculation for the result. And so let's capitalize on that. And here it is, just sort of summarizing. We were computing the columns of the Jacobian matrix, and you can see right here these columns of that Jacobian matrix. They are the partial derivatives of the function in question. If the function has multiple variables, right? If this function is, into Rm, right, then there will be m entries in each of those partial derivative vectors because there are m variables to take partials of. Okay. All right, and there is your matrix. So here's the same thing said in a slightly different way. The first column is all of the partials with respect to x1, and writing that out explicitly. Okay, well here's that. Here's that first column. Come on, highlighter. There's that first column. Note that all of the partials are with respect to x1. And notice that we're just expanding and saying, well, that function f has components f1 and f2, etc., down to fm. So just writing it out in components, there is that first column, giving us this, and likewise for the other columns, right? And that gives us this other nice point of view on the Jacobian matrix. It's just an organized array of all of the partial derivatives of all of the output components taken with respect to all of the input components. So take all the different partial derivatives of all the components and write them in an array, like I say, an organized array like this, and bam, that is the magic matrix that computes directional derivatives for you. Okay. All right. There's one asterisk before we get to some examples. One asterisk I want to point out. As a result of how awesomely convenient this is, we'll see examples in a moment. As a result, students tend to dive in a little too fast on the Jacobian matrix. I do want to remind you of this condition. The Jacobian matrix represents the derivative transformation. The derivative transformation only exists for a differentiable function. Your function has to be differentiable. You have to note that your function is differentiable before you start going around pretending like it's differentiable. Right? Not every function is differentiable. There are some functions where, and this is super awkward, but there are some functions where you can compute, no problem, all of these partial derivatives. No problem. These are all fine individually. But the function is not differentiable, and so assembling them into a matrix doesn't make any sense. It's absolute garbage, meaningless, useless, unreliable nonsense. So don't make that mistake. Right? An easy landmine to step on. Don't start taking partial derivatives of something to assemble into a matrix to use as if the function's differentiable, unless you know it's differentiable. So, and again, how do you check differentiability? Well, you look for continuous differentiability. Okay. Yeah. So, example. Let's look at this function right here, and let's look for the velocity vector of the output. Well, velocity vector of the output, we know it's going to be a directional derivative. That's what directional derivatives are. That's old news. That's from Friday, right? Directional derivative. Now we're given a base point. We're at the point pi comma pi over 2. We're moving with a certain velocity, 3 comma 5. And so, you look at this question as stated. You could totally take this as a directional derivative question, a section 4.3, plug and chug question. Now let me point out. I'll come back to that. So let's go ahead and do this computation. I'm not going to do it the old-fashioned way, though. Now I'm going to use the differentiability. Notice that these functions in here, they are all differentiable. In fact, they are all continuously differentiable in partial derivatives with respect to all of the variables. Take any one of these components. Take its partial with respect to, I don't care, x, y, whatever. Compute all those partial derivatives. They're all continuous. So that function is continuously differentiable, and therefore also differentiable, and therefore I can compute this with a derivative transformation or a Jacobian matrix. Okay. So all I got to do is take those functions, take some partial derivatives, right? The Jacobian just made up of a bunch of partial derivatives. Y'all can do partial derivatives. I won't walk you through those details. But do notice that first we're taking these three functions. To get the first column, we're taking the derivatives with respect to the first variable x. To get the second column, we are taking the partial derivatives with respect to the second variable y. So make sure you can do that. By the way, I've said this a bunch of times, but I feel like I have to. Don't forget, in the prerequisite trail of this course, Calc 1. Right? So all of the derivative rules, all of the antiderivative rules, all of that I am assuming that you are good to go. So make sure that you're solid with the chain rule and product rule and all that business. Okay. So yeah, there's our Jacobian. We're interested in what's happening at this particular point, I highlighted the wrong thing. At this particular point, pi comma pi over 2. That's where we want to compute the directional derivative. So I need to evaluate that Jacobian at the point pi comma pi over 2. You plug that in, and the Jacobian, the thing that you multiply by the velocity, the thing that represents the derivative transformation, there it is. Numbers. And then, multiply by the velocity vector. Color choices. Multiply by the velocity vector. That's been coming along for the ride all along there. And there is your directional derivative. Now, so the other thing I was going to say about this example, though, yes, it gave us an alternative way to compute this one directional derivative. But you could imagine also a scenario where, look, the thing is, I'm at this point, but I'm not always moving with that velocity. I might be moving with, a bunch of different velocities. What if I have 7 different velocities? I need to compute the directional derivative, right, with all of those 7 velocities at that same point. Well, then you just put those 7 different velocity vectors in here. And you're multiplying by that same Jacobian matrix. If you're looking at the same function at the same point, it's got the same Jacobian matrix. And so this not only, I think, streamlines at least a little bit one calculation, this massively streamlines if you have a bunch of calculations. Big computational win. And I see I'm out of time here. I'm going to let y'all read the remaining examples here. They're not importantly different from what we just talked about. So we are done through section 4.7, and I owe y'all an email formalizing that. And if y'all can stick around for a couple minutes, I'll hand back homeworks. Okay, see you later. Let's see here.